Okay, let's take a look at a couple of convolution examples. So in the first example here, let's look at problem 2.4-4 from the end of chapter 2, and we're asked to find the result of convolving e to the minus at u of t with e to the minus bt u of t. Okay. There's a table in your textbook, actually on table 2.1, I think on page 177, that lists some common convolution pairs, and this particular pair is in that table, but we'll go through the process of actually explicitly evaluating the convolution integral, because you won't find all pairs of functions, of course, listed in that table. So we'll let x1 of t equal e to the minus at u of t, and x2 of t equal the second function, e to the minus bt u of t. And from our convolution integral, writing that down, in the general case, it's the integral from minus infinity to infinity of x1 of tau, x2 of t minus tau, d tau, and then substituting for x1 of tau, so we have that expression right here. We just need to substitute tau for t, and we get e to the minus a tau u tau, and similarly we substitute t minus tau in for t in the x2 expression, and we get e to the minus b t minus tau u of t minus tau d tau. And now u of tau, of course, is a function that looks like this. U of tau as a function of tau. We're familiar with that. It's 1 for all tau greater than 0 and 0 for all tau less than 0. So because that's in the integrand here, that would change our lower limit from minus infinity to 0. U of t minus tau as a function of tau looks like this. It's actually a time reversed function. So this is u of t minus tau, and sketching this as a function of tau, and it's shifted to t. Okay. So this would change our upper limit of our integral to t, as long as t is greater than 0. If t is less than 0, the product of these two functions is 0, and the integral would be 0 everywhere. So we can replace our limits 0 and t. We have e to the minus a tau. Of course, u of tau actually determined our lower limit, and then I'm going to distribute the b here. I'll have e to the minus b t, and then I'll have will be plus b tau, but I can write that actually using a property of exponents as e to the plus b tau. And then the u of t minus tau determined our upper limit, integrals over tau. And again, this is the result for the case where t is greater than 0. Okay. If t is less than 0, the result is 0. So I'll take one more step here. I can factor out this e to the minus b term because I'm integrating over tau. So factor out e to the minus bt, integral of 0 to t, and then I can combine my two exponents here, I'll have e to the b minus a when I combine the b tau and the minus a tau term, integrating over tau. Again, remembering that this is just the result when t is greater than 0. So going on to the next board, I can do that exponential integral. The result is e to the minus bt, the term in front, and carrying out the integral, I'll get 1 over b minus a, e to the b minus a tau. Evaluating this at 0, my limits 0 and t, and this becomes 1 over b minus a, e to the minus bt, e to the, evaluating this at tau equal to t, I'm left with b minus a t, and evaluating it at tau equal to 0, e to the 0 is 1. Okay. I can write this in a slightly simpler form if I multiply the e to the minus bt term through. Here I've got a plus bt, so that will cancel. And this simplifies to the form e to the minus at minus e to the minus bt over b minus a. And again, this result is valid only for t greater than 0, so I can incorporate that by just multiplying by u of t, because this will be equal to 1 for t greater than 0, and it's 0 for t less than 0. So this is the result of convolving those two exponentials. Switched exponentials, e to the minus at u of t and e to the minus bt u of t. You can find that pair in the table of convolution pairs and verify that the result we get by direct evaluation of the integral agrees with this. Let's take a look at one more example. Problem 2.4-7. Here they give us an impulse response. H of t is equal to e to the minus t u of t. This is actually the impulse response of an RC circuit where both the resistor is 1 ohm and the capacitor is 1 farad, and the input is a voltage, x of t, and then the output is the voltage across the capacitor. So the impulse response of this circuit, again letting x of t be an impulse, and determine y of t. Of course, when x of t is an impulse, y of t is h of t. This is the result when you apply an impulse as the voltage here in x of t. So we're asked to find now for this circuit the output for several different inputs. When the input is u of t, and we can find this pair in our convolution table. It's also a special case of the problem where that we just worked. So if where we could let a be 0, and because e to the 0 would be 1, and then let b be minus 1, and so we can treat it, find the result by making that substitution, or again just look it up in our table, and we get the result y of t is 1 minus e to the minus t u of t. And a quick sketch of what that would look like is actually like this at t equal to 0. This starts out at 0, okay, and as t becomes large, e to the minus t goes to 0, and so this thing approaches 1. Okay. And this kind of agrees with what we know about circuits. We know that if the capacitor is initially uncharged, the voltage across it would start at 0, and then if we apply a unit step in this case, we know that the voltage can't change instantaneously, so it'll start at 0, and then if we've got 1 volt applied, we know that the capacitor voltage will eventually charge up to that 1 volt that's applied at this at the voltage source. And if we have an exponential voltage source, and then again we can find this in our table of convolution pairs. Here we can't use the previous result because A and B would both be equal and would both be equal to 1, and so we'd be dividing by 0. So this is a different convolution pair, and so you look up in the table the case where the two exponent terms are the same, and you'll find this result. Y of t then is t e to the minus t u of t. Okay. And just a note here about the starting time. The impulse response for this circuit is just a decaying exponential switched on at t equal to 0. So it's the impulse response h of t starts at 0. This particular input is actually identical. It's a decaying exponential that starts at 0. So the output in this case would be at the sum of the two start times. The output should also start at 0, which is what we see here. Of course, these aren't finite duration pulses. They're both infinite in extent, so the output is also infinite in extent. Part C is just a different decaying exponential as the applied voltage. Again, we can use our result from the previous board. We get e to the minus t minus e to the minus 2t. Here I let a be the minus 1 term and b, or a be 1 and b be 2, and then we have the denominator minus 1 minus a minus 2, or this is all times actually u of t. So minus 1 minus minus 2 is just 1, so this simplifies to e to the minus t minus e to the minus 2t u of t. Again, it would have a starting time of 0. And in part D, it's the most complicated part, x of t is a sinusoid frequency 3 radians per second, omega equal 3 radians per second, and it's switched on. Okay, so it starts at t equal to 0. So if you look through the table, you won't find one involving a sinusoid, and if you recall, what we're convolving with is h of t is equal to e to the minus t u of t. But you will see in the table there's actually a cosine function. So we could actually represent a sine as a phase shifted cosine. It's 3t minus 90 degrees. That's equivalent to a sine u of t. And then now you can find in the convolution table the result of convolving a switched cosine with a switched exponential. I'll let you work through the details here on finding the various angles, but y of t in this case is 1 over the square root of 10, and then you have cosine, and then the values that get plugged in are minus 90 degrees and then plus 108.4 degrees, and then that's multiplied by this exponential term, and then we have cosine 3t minus 90 degrees plus 108.4 degrees. Okay. All times u of t, so the output would be switched on. So we see in this particular case the output, of course this term is just a constant cosine of a particular angle in degrees. There's no time dependence here, and it's multiplied by this decaying exponential. So in this particular case, the zero state response, or the response due to this particular sinusoidal input, consists of an exponentially decaying term, and then there's this sinusoidal term that is constant in amplitude, has an amplitude of 1 over square root of 10, so it would continue on forever. Of course, our input continues on forever as well. So that's how you can get some of these results using the convolution table. Next lecture, we'll spend a bit more time directly evaluating the convolution integral via a method known as graphical convolution.